All right, we're looking at an Invaders problem, two-part, that deals with phosphoric acid, and then secondary, it deals with the buffer. The very first part just says, what is the pH of a 3.4 molar solution of phosphoric acid? All right, so we've got a 3.4 molar solution of phosphoric acid. All right, now this is a weak acid, right? Because look at the H to O ratio, and you'll see that it's not 2 or more. The only way to find the pH of a weak sample is going to be to add it to water in a rice table. So I'm going to take, because that's what it wants to know, is what's the pH. So I'm going to take the H3PO4 and add it to water. All right, and we are going to end up letting this acid do what it's going to do. Acids want to donate, so let's get rid of one of those H's. And it donates it to our amphoteric water. So hooray, there's some hydronium. Now remember, we're finding the pH of a weak sample. This is going to happen in a rice table. I stands for initial concentration. It's given to us, 3.4. Water does not affect equilibrium. All right, and in this analysis, there is not any initial concentrations of those guys. All right, we're gonna track our change. I plus C equals E. All right. So cool. I want to know the hydronium concentration because that will directly link to pH, right? So this is an equilibrium deal. I do have a given Ka value, which is nice in the problem. The problem says that Ka is 1.7 E negative 3. All right, and I know that K equals products over reactants. The products is X squared. The reactants is 3.4 minus X. Again, make sure you stop me if you don't like something that I do. All right, this is from a unit ago, so. I'm going to cross multiply into a 0 equals. And we'll get 0 equals X squared going this direction. And then remember, I'm going to reverse the signs this direction because they would start where the 0 is, but I want to move them over to where the X squared is. So when it multiplies times that negative X, I make it positive. And when it multiplies times this positive factor, I make it negative. You put that into the solver, and you'll find that X is equal to 0.0752. This X is the molarity of the H3O plus. That's really nice because that's a strong sample. So the negative log of this value is going to equal the pH. And that answers the first part of the question, but that's review from last unit, but you need to obviously always be able to do that. Is that okay? Well, let's keep reading then. All right, it says a buffer is prepared, exciting, by adding some of this phosphoric acid to a solution of sodium hydroxide. Okay, so let's add that to the solution. Let's watch it happen. I need all this space. There we go. Okay, so we are going to have an invasion take place now by a strong sample, which is sodium hydroxide. We know that's strong. All right, so that's going to be my OH minus is the strong that it says is going to invade the phosphoric acid that we just got done analyzing. Acids want to donate, bases want to gain. All right, so when we move that proton over, you'll get water. All right, but you'll also get the ion here. All right, and there's the buffer that it was talking about in the problem, right? Because that's the weak acid we just got done analyzing, and there's its conjugate base, which is, minus an H. All right, let's take a look at the values that it gives me. All right, it says that we are going to have, of the phosphoric acid, it says, oh, look, it gives us liters. It never does that. 0.63 liters. All right, so this is going to be all right, 0.63 liters times his molarity of 3.4. Right, that's what was true a moment ago, right? And if we multiply those together, we are going to get 2.14 moles. All right. The hydroxide, as I read, is sitting at 0.0890 liters. All right. And we want to multiply it by his molarity, which is listed at 0.5. And that's going to give me 0.0445. So there's my mole comparison on the invasion. All right. Of course, the water doesn't matter. All right. And these were the only items that were mixed together. So there's not any moles of him right now. This is not a rice table. I'm just tracking moles. So have them fight, subtract the smaller number. All right, we're going to run out of that dude. We're going to end up with 2.1 moles here. And of course, it's going to shift up on the other side. There's usually more questions in tutoring. It feels like a class. I now have mole counts of a buffer. Henderson equation is what we would use to continue to the pH. This one's a hydroxide concentration. That's evil. But anyway, we'll finish. So let's use the Henderson where we're going to go negative log. Whoops. That's right, but pH equals. All right, pKa. So it's going to be negative log. I have the Ka. Remember, it was given to me. All right, sitting there at 1.7 E negative 3. Plus the log, right? And remember, we can use the mole counts in the Henderson equation only, right? Where it says to go to molarity, but we can skip it. So we need to do ion over weak. There's the ion. Over the weak sample. This is going to spit out a pH. When you run it, I'll give you a moment for those of y'all that want to verify. Why not? I haven't done this in a while. Yay, it still works. I get 1.096. Now, Heidi, this is where the problems, you're the one that asked, this is where it gets kind of mean, because it doesn't want pH, it doesn't even want hydronium, it wants a hydroxide concentration, and that's just kind of ridiculous. But whatever, we can figure it out. So what I know is that if the pH is this, the pOH going to 14 must be 12.904. And then I have to remember that in order to go from a pOH to an OH minus concentration, since they're directly connected, is to simply go 10 to the negative value